In this video, we will talk on the types of data that a C program can have, how they are specified, what notation is used for each type, the format specifiers of each type to be used with the function printf, and then we'll do some practice on a line compiler to wrap it up with a clear understanding. Let's talk on how we represent numbers in binary system. So let's say for instance that we have 8-bit data, that is 1 byte. So we have the least significant bit and the most significant bit. Just as in our decimal numbering system, this is a least significant digit because it is the units. So it is the number 5, and this number 1 is actually 10 because it is in the tens. This 3 is actually 300 because it's in the hundreds, and this one is actually 1000 because it's in the thousands digit. So the same happens here. This is the least significant with the least value, and there are another with higher values. Okay. So let's say for instance that we're going to write the number 0. So it's all zeros in every bit. And when we want to write the value of 1, it will be the number 1 in the lowest bit. However, if we want to write 2, it will start incrementing every bit and doing the carryover to the next most significant digits. Okay, so it will continue so on and so forth. But how do we know what's the maximum number that can be represented with 8 bits? So what we do here is taking into account that whenever all of these bits reaches the value of 1, it will be the maximum value. Why? Once all of these bits equal to 1, we do not have the possibility of do a carryover because we have just 8 bits. So the maximum value that we are going to have here is 255. How do we know that? Well, we actually translate every bit in every position to its actual value, depending on the digit that it occupies. And all of this is done by taking the powers of 2. So here are the numbers that they represent. If we do the addition of all of these individual bits, we have a result of 256. But what's happening here? We do not count from the number 1, but we start from the number 0. So we kinda have to subtract 1 unit from this result to have the actual maximum value that will be represented in 8 bits. So we're going to have from 0 up to 255. So here's the formula. You always subtract 1 because we always start from 0, not from 1. And this is the maximum value that we can have in 8 bits, as I told you, because it's the maximum value that can be represented because we do not have any more bits available. So that's for counting just positive numbers. What happens if we need to count negative values? So this datum is going to be called signed, a signed datum, because we are going to take into account negative values. So when we specify that a datum to be signed, what we are going to do is actually split that number of 256 that we had previously into two halves. So one half, that's going to be 128, is going to be available for the maximum amount of numbers that we can use with negative values, and the other half, that is well, the half of that number, that is 128, will be used for non-negative numbers, that is numbers including the 0 for these 128 non-negative numbers or positions. So what you basically do when you use a datum as signed is use the maximum amount of bits, that is 8, and subtract one unit, and then the resulting number will be the exponent to find the maximum values that you can have in the negative side and the positive side, or not negative side, including the 0. So what happens here with the 18-bit data? It is the same. You find the 16th power of 2 minus 1, and there you have the maximum number that you will have in this 16-bit datum. You start from 0 up to this amount of that you see here. So that's the maximum value that you can store here. You can surpass this value, otherwise it will throw an error. You don't have more space for greater amounts. There is a unsigned datum of 16 bits, but what happens if we want to use values with negative numbers, that is a signed datum? We'll do the same, we'll experience the same effect. We will have to split this maximum number into halves, and we're going to have the half of this number for the maximum amount of negative numbers, and the other half of this number to the maximum amount of positive or non-negative numbers, starting from 0 again. If you see here, if you this amount of positive is 1, is exactly a 1 unit lower than this one. Actually, this is because we include the 0 here, so it will be the same amount of non-negative values with 32,768, including this, which is non-negative. So it will split in two halves of negative and positive values equally. So in 32-bit data we have the same. We use the maximum number of bits as the exponent in the power of 2, and minus 1 again, and here we have the maximum number that we can store with positive value. However, if you want this amount to be signed, we split the same maximum number into two halves. So the half of this number is going to be for negative numbers. The other half is going to be for the maximum positive value that you can store in this 32-bit data. And let's continue. What happens now with numbers that have fractional part, that is real numbers? Well, they need to be written in at least a 32-bit data. So say for instance that we have this number here, which is 478, this digital point, and we want to express it in digital format. It is coded in a more complex manner. So it will take the fractional part, just like if it is written in scientific notation. It will take the non-fractional part and will store it in a certain position, an amount of bits, and the fractional part will be stored in some other position that occupies a number of bits, and then the power of 10 is going to be stored in some other position and amount of bits. So we basically take the non-fractional part, fractional part or mantissa, and the exponent, that is the power of 10. The next one is, for instance, the character data, that is information that represents a letter or a special symbol. And what will we have here? We are going to use the easiest one, which is the ASCII code, which is 8 bits long data, and we basically take this information. If you told your program that it's going to be character data, it's going to use this number that's going to be stored here, and we'll find its letter equivalent. So it's taken internally as a number, but it will result in a equivalent order that will tell you what the character or the special symbol is. In C language, before you can use data either to read or store values, you must create them first. These data are called variables. To create them, you must specify the type and a valid name. Each data occupies different sizes in memory. It is interpreted differently depending on the type, and the operations permitted to be applied to it are different. You can't store data of one type in variables of different type. This will cause errors, and some operations do not work for some types. That's why it is important to know the differences. Let's start with the basic data types. Here we have the keyword that we are going to use. So char stands for character, so a written symbol. It can be a number, letters of the alphabet, or a special character. However, it can represent small amounts of numeric values like these ones that are showing here. Um, let's have a look at previous lessons that we had. As you can see, a character data also may have a numeric value, binary. It equates a particular written symbol, that is a special symbol or letters of the alphabet. So the next one is the integer with this keyword int, and this is the ranges of numeric values that it can take, format specifier, and the number of bytes it occupies. The char data type is the smallest, occupying just on 1 byte. This integer 4 bytes. Float, it's a type of data that allows to write real numbers, that is, numbers with fractional parts, and it has up to 6 decimal digits. The next one is double, which is uh, another variable data type to that is capable of storing this type of numbers that have fractional part, and it has 15 decimal digits, and this is the format specifier. As you can see, it occupies way more bytes. So let's start by applying this in our code and see how it works, this format specifier with our printf function.